Hi everyone, welcome to our video on rational functions and their asymptotes. So rational functions have this special form where it's a polynomial divided by a polynomial. Let me box it, there we go, a polynomial divided by a polynomial, and we usually write it as p of x over q of x for those polynomials. The domain for these problems is where the denominator, let me say that again. So the domain is all real numbers except for the x values that make q of x equal 0. So that the other way, let me write it like this. The domain is where, let me just use the words too. The domain of these rational functions is making sure the denominator cannot be 0. So I abbreviated denominator. Denominator cannot be 0. Okay, so let me box that instead. That's better. Okay, so here I wanted to use the math notations, but in words I think it's better. The domain is where the denominator cannot be 0. Okay, so the rational function is undefined when that denominator is 0. So there'll either be a gap in the graph in the form of either an asymptote, the vertical asymptote, or a hole. So these asymptotes, we'll show them visually, they're just going to be guides for the direction of the graph. Okay, so we'll see that real soon. So let's first just find the domain of these two problems. So domains are special problems. We see that it's rational, so that means all we have to do is make sure the denominator is not 0. So x plus 6 cannot be 0. And then we solve this the same way as if it was a regular equation. So we would just subtract the 6 over, and we would get x cannot be negative 6. Now they will want these answers to be in interval notation. So that means I'm going to sketch this picture real quick on a number line. So this is our x number line. And then the only thing that's important to me is negative 6. So that's the only thing I put on the number line. The not equal symbol means you put a big open dot where that value is. And then this is saying this is the only thing that you cannot have. That means everything else, let me actually even change it to blue, everything else on the graph would be fine. So I'm showing in the arrows from left to right means you could plug in any other x value and you will get a y value. And so if I go far left, that's to negative infinity. Going to the far right is positive infinity. So this is the visual of our answer. The final answer is just putting this information in left to right using parentheses. Okay, so it would be negative infinity with a parenthesis on it, comma, to negative 6 is where there's a problem in the function. And then we usually use the union symbol to say there's more to this answer. Okay, so after negative 6, so a parenthesis negative 6, it goes to the right forever, so infinity. Okay, so that's what it means. This is the visual of the answer, and you could even put, so I put negative 6 down below, but you put it right here and see, there it is. With the middle gap in it, that's bad. So that's where we show, hey, something at negative 6 is going on. These parentheses mean that the negative 6 is not allowed to be plugged into this function. Okay, but you can plug in any other value that you want into this function to get another y coordinate. All right, so number 2. No, and also notice with this rational function, I mean, I could look at the numerator, it's just 5. That means there's no problem with the 5. I have no issue with it, and I can move on. Same deal with this g of x. The x squared minus 9, I know I can plug any x value in there, and no problem will come about. Okay, so there won't be any undefineds or anything weird. But this bottom one, x plus 3, that cannot be 0. X plus 3 cannot be 0. So that's setting the denominator not equal to 0. And then just like before, well, I could subtract the 3 and then get x cannot be negative 3. Okay, however, that's not the form of our final answer, so this is why I just make a very quick sketch to get the visual. So negative 3 has the open dot, and then from left to right, everything else is good. Okay, so starting at negative infinity, I have negative infinity and then comma to negative 3, and then union symbol to show that I've got more. Negative 3 to infinity. So this is again just telling you you could plug in any number you want except negative 3. All right, so let's see the other thing that we could do with these vertical asymptotes. Okay, so vertical asymptotes would occur where the denominator is 0. Okay, so it's kind of like a domain problem. So vertical asymptotes, for abbreviation, is when the denominator equals 0. So notice these are going to be pretty much the same problem. I just have to make sure to use equals instead of not equals. All right, so for instance, on number 1 here, it's rational again, so we see it's a rational function. X squared minus 64 in the numerator is fine. That I could just move on from. This 8x in the denominator, let me even label it vertical asymptotes, is when the denominator equals 0. So now I do 8x equals 0. And then, well, we could solve this. If I just divide by 8, we would get x is 0. 0 divided by 8 is 0. Okay, so that is the final answer. So these ones we leave in the equation form. All right, that's that. Number 2, I have 2x in the numerator, which again is fine. There's no problem with that. The main issue is the denominator, and that's where we can find our vertical asymptotes by setting the denominator equal to 0. Okay, so this is a quadratic that can be factored. So if we factor this, the way that I factor is I multiply the leading coefficient, which is 1, times the last constant, which is negative 12. And then from there, we can find all the factors by using, I just call it a factor tree. There we go. So these are all the factors. So it's whatever times something that does equal 12. And then afterwards, I need to find the signs that when I add whatever pair up, it needs to equal negative 1. Okay, so there's 1 there. So let me put the 1, and there's 1 there. Okay, so that's that first one getting multiplied, that one. And then now I need to find the pair that adds up to negative 1. Okay, so that looks like, and so I choose the signs on these. So it looks like I need to do that. Because positive 3 and minus 4 would add up to be negative 1. Also notice that when these multiply, it does match the negative 12. Okay, so I have to choose the signs to make these correct. Okay, and then now that I do have it, I can rewrite it as x. So I just write it with just regular x here. And then I plug in those factors. So plus the 3 and then minus the 4. So that's the quick way to factor. So there's more on factoring in other videos if you do need the help. Okay, but factoring is something that is very common in math. We do it a lot. So not all the time, obviously, but it's always good to know how to do it. So if you are rusty, check out those videos for sure. All right, now I can. So when it is factored, once it's set equal to 0, I can split each factor and set it equal to 0. So that's called the zero product rule, which then allows us to solve each of these real quick. Just like that. Okay, so then we would get x is negative 3. And we would get x is 4. So this problem, number 2, has 2 asymptotes, 2 vertical asymptotes. Okay, so that's that. So that's how we can find them. So notice the domain problem of a rational function and a vertical asymptote of a rational function are very similar, setting a denominator either equal to 0 or not equal to 0. All right, the other type of asymptotes that are involved in these problems are horizontal asymptotes. There's 3 cases that can occur. So we first again start with a rational function where we have some polynomial divided by some polynomial. The 3 cases are, well, let's go through them. Number 1, a horizontal asymptote of y equals 0. So that will be an answer. A horizontal asymptote of y equals 0 when the degree, so let me write it like this. So all we care about is the degree. It will occur when this degree is bigger, the denominator's degree. Okay, so that's all we have to look at. That will be under this big bolded underline is the answer when this denominator's degree is bigger than the numerator's. All right, there's a horizontal asymptote of y equals, and just in words, it's the leading coefficient of p of x divided by the leading coefficient of q of x when the degrees are the same. Let's write it just like that. And then the last type of asymptote is, well, or last type of horizontal asymptote is there is none. So that would be our final answer. What would occur is called a slant asymptote, which is something that we don't really need to worry about if they're asking about horizontal only. Okay, so it's either no horizontal asymptote when, let's write it like this again, when we have our general form when the numerator is a bigger degree. Numerator is a bigger degree. Okay, so there's the three cases. Okay, so they're very fast problems as long as we catch whatever rule needs to be applied. So for instance, on number 1, so it's saying find the horizontal asymptote if it exists. Number 1, I can see that this is a bigger degree than up top. This is a degree 2. This is a degree 1. So remember, the degree is just whatever the highest power is on our x. And I put a little 1 there just to put it. But squared is bigger than 1. And you don't need to actually find the degree. You can just eyeball these. This is definitely a bigger degree. So this is our rule number 1. So the horizontal asymptote, we'll abbreviate it as HA, is just instantly y equals 0. That's it. Done. Okay, for number 2, I'm looking at these. Make sure it is in descending order. It does look like it's in descending order. Notice I use T, but that's okay. It doesn't have to be X every time. But I can see, okay, and I'll even let me highlight that first one just to mark what was important. Let me highlight these. So I see those are the degree. They're both degree 2 then. So that means they're the same degree. I'm just going to mark it like this. Same degree. Which means my horizontal asymptote is found by taking the leading coefficient. So my leading coefficient of the numerator is -2, divided by the leading coefficient of my denominator. Remember, this would have a 1 right there attached to it. So that means 1 is in my denominator. And then, well, we would simplify. This would be just y equals -2. On these horizontal asymptotes, make sure that it is y equals a number. Okay, so don't just write 0. Don't just write -2. Okay, because this is telling us that it will be a line, a horizontal line, when we start to graph, which will be in the next video. Okay, same deal with the vertical asymptotes. Make sure it is x equals a number. Let me go ahead and even box that. So notice all my answers for the vertical asymptotes were x equals a number, because that will show us that it is a vertical line when we start to graph these things. Okay, but one other, number 3 here. Looking at my degree, notice my numerator's degree is larger than my denominator. So I know that this one has no horizontal asymptote. That's rule number 3 right there. So these went in the order of the rules. Okay, so this one, and just to mark it, I could just put bigger degree as needed. The bigger degree in the numerator. All right, so no horizontal asymptote. Okay, so that's our video so far, or that is our video, on the types of asymptotes and domains. Okay, so notice with vertical asymptotes, the denominator is more concerning. Same with the domain. So domain and vertical asymptotes are similar. You're focused on the denominator. Horizontal asymptotes is a comparison of degrees between the numerator and denominator. All right, so that's that. Okay, so if you do have questions, please let me know. Otherwise, thanks for watching, and I'll see you again soon.